Unit 5A, Thermochem, Moodle Quiz 4. We're going to do problems 7, 9, and 12. Here's problem number 7. An unknown mass of ice at negative 15 degrees is added to 32.2 grams of water at 25 degrees Celsius. So here's what this looks like. You have water and some ice. We do not know the grams of ice, so that's our question mark, X grams of ice. But we do know that here's our water. It is 32.2 grams worth, and it is at 25 degrees Celsius. The question asks, and the ice is at negative 15 degrees Celsius. How much ice must be used so that all of the ice melts and the final temperature of the mixture is 0 degrees? And so by the time both of these have reached equilibrium, we have a final temperature of 0 degrees Celsius. So let's kind of look at what's happening, but in the form of a graph. So here is solid, then here is melting, and then here is liquid. So here's where melting occurs, and right there it would be at 0 degrees Celsius. So all the way across here is 0 degrees Celsius. And we have two things that are happening to our ice. First, the ice is at negative 15 degrees Celsius. So first we have to actually get the solid ice to reach the temperature where it will start to melt, and then we need all of the ice to actually melt. And so we'll call this segment A, and I'll call this segment B. We have water that's at 25 degrees Celsius, and the water is going to cool down until it also reaches 0 degrees Celsius. And we'll call this segment C. So the amount of heat that it takes to get the ice to the point of melting, plus the amount of heat it takes to melt the ice, should be equal to the amount of heat that is lost by the liquid water. So we can write our equation based on this. So I'll start with segment A, where the CS times G times delta T, because you'll notice in segment A there is a temperature change. This is for my ice, plus, and I'll call this segment A, plus segment B, all of the ice should melt, and so that would be the moles times the delta H of fusion. So we'll call this ice melts, and that's segment B. That should be equal to the negative of segment C, which is CS times G times delta T for the water. So that's segment C. Okay, so now that we have our equation figured out, we can plug in our values, and here we're given that the specific heat for ice is 2.092 joules per gram degree Celsius, times, I don't know the mass of the ice. So I'll call that X, that's grams of ice, times the change in temperature. Now, from here to here, the final temperature is 0 degrees Celsius, minus the initial temperature is negative 15. So be careful to minus your negative. It's going to end up being added together. But missing that sign will change the entire answer, of course. We're going to add this. So all of that is being added to the moles of ice. Now, I don't know the mass of the ice, and recall that moles is equal to the grams divided by the molar mass. And so actually, I'm going to insert that here and say I don't know the grams of ice, but I do know the molar mass is 18.02 because it's ice, which is water. So there's the moles, and that's going to be times the delta H of fusion, which is given here, 6,008, and that's joules per mole. So we have our CS times G times delta T plus our moles times delta H equals the negative, and our specific heat for water is 4.184 joules per gram degree Celsius, times the mass of water, 32.2 grams, times the change in temperature. The final temperature is 0, the initial temperature is 25, so 0 degrees minus 25 degrees Celsius. Okay, so now we have our entire equation set up, and so we can plug this into our calculator and solve. I'll do a little simplifying first. If I take 2.092 times, this turns into a positive, times 15, we get 31.38x. Plus, I'm going to take 6,008 divided by 18.02, and that's going to give us 333.407x equals, multiply 4.184 times 32.2 times negative 25, and there's this negative, is going to give me 3,368.12. I'm going to combine these two x's, and I'm going to get 364.787x equals, and then divide both sides to get x equals 9.233 grams of ice, which is letter C. What is the final state of the system after 15 kilojoules of energy is removed from 150 grams of water at 1 atmosphere? The water has an initial temperature of 20 degrees. So let's see what we're working with here. Here would be a solid, here would be melting, and here is the liquid phase. At melting, it is 0 degrees Celsius. We have water that's here, and it is 150.0 grams worth, and it is at 20 degrees Celsius. So the question is, if I take 15 kilojoules of energy from this water, then what would the state end up being? Well, let's test out the situation first. How much energy would it take to get the water down to its freezing point, 0 degrees? Let's just see that. So I can use Q is equal to CS times G times delta T. And so it would take, so water is 4.184 times 150 grams times, and we would have a final temperature of 0 degrees minus the initial temperature of 20. And so when I do this math, I get a value of negative 12,552. Keep in mind this is in joules, so I want to change it to kilojoules by dividing by 1,000, and that'll get me 12.552 kilojoules. So what that means is, of my 15.0 kilojoules, it would take 12.552 kilojoules to get it from this point to beginning to freeze. So how much do I have left over of my 15.0 kilojoules? I will have 2.448 kilojoules of energy left. So it is going to get down to the point of freezing, and it's going to actually go past the point of freezing. But by how far? Is it going to go just freeze some of the water, or is it going to freeze all of the water? Well, you can test and see how much energy would it take to get from this point to this point. So Q is equal to the moles times the delta H of fusion. And so that would be to determine, am I going to actually freeze all 150 grams of this water? Well, let's see how much energy that would take. 150.0 grams divided by its molar mass, 18.02, times the delta H of fusion, which is 6,008 joules per mole. And I'll go ahead and convert that from joules to kilojoules, since that's what we are operating with right now. So when I do this math, I get a Q equal to 50.011 kilojoules. And we only have 2.448 kilojoules left, so there's no way we're going to freeze all the way to the end. So that's not going to happen. So now the question is, all right, well, it's only going to freeze some of the water, and how much of it is going to become ice? So I can take the amount of energy and use it with the equation, again, Q equals moles times delta H of fusion. And I know that we're going to only use up 2.448 kilojoules of energy is equal to how many grams of ice will I form, the mass is 18.02, times the delta H of fusion, which is 6,008 joules. Convert that by dividing by 1,000, and so now we'll have that as in kilojoules instead. And so when I do this math, I get a grams of ice equal to 7.342 grams. Now, if you look at the answer choices, since we know that we were going to end up somewhere right here on our graph, then we can process of eliminate this, that we're going to end up with 150 grams of ice at negative 29. That would be a temperature way down here. That's not going to happen. C and D are both saying it'll remain water, and we would have stopped before we get to the point of freezing. Well, we know C and D are out. An equilibrium mixture of 12.59 grams of ice and 137.4 grams of water. So basically it was down to A or E. We were going to end up in a state of equilibrium, but how much ice were we going to have versus how much water? And so now we know how much ice we were going to have, 7.342, which makes our answer E.